I'm now going to show you linear time sorting algorithms, and we're going to look at 3 such algorithms: counting sort, radix sort, and bucket sort. So how is this possible? So the only reason this is possible is they're not comparison based. So the decisions that these algorithms do are not only based on comparing two numbers. So these are not comparison based sorting algorithms, and we will also need extra assumptions on the input to get a faster running time. So let's start with counting sort. And the idea of counting sort is very simple. I mean, imagine you have an array of zeros and ones, for instance. How would you sort it? You would sort it by counting. You would count 1, 2, 3, 4 zeros, 1, 2, 3 ones. At this point, you know that you will want to place all zeros here and all ones here. Note, what you don't want to do is now just write zeros here and write ones there, because there might be additional information attached to these numbers. So you really want to move the zeros into the first part and the ones into the second part. Counting sort generalizes this idea. So the input is an array of numbers, of n numbers, and we assume that these inputs are in a range of 0 to k. So in my example, k was 1. Now k can be larger. And the main idea is that for every number in the array, so for every ai, we count the number of elements that are less or equal to ai, because that will tell us where to place ai. So the number of elements less or equal to ai, we will call this the position of ai. And the actual index is then that position minus 1, because we said equal to, so we're counting the element itself. Of course, we have to be careful about elements with the same value. Therefore, we define position slightly more carefully. So we say the position for ai, so position of I, is the number of elements that are less than ai in the whole array, plus the number of elements that are equal to ai in the array up to ai. And keep in mind that we're using this notation with a colon, which is saying from 0 to ai plus 1, not including I plus 1. So this is our notation to say subarray from 0 to I. So how does this look like? For instance, if I'm looking at this 5 here, the position of that 5 is a number of elements smaller than 5. So let's count. 3 is smaller, 4 is smaller, 3 is smaller, 3 is smaller, 3 is smaller. So it's 1, 2, 3, 4, 5, plus the number of elements equal to that 5, but only in the subarray up to that 5. So that is 1, 2, 3. So the position is, in this case, 8. And you see here, if I count 1, 2, 3, 4, 5, 6, 7, 8. So it's the 8th number, meaning that the index will be, so the index here is 7. So position minus 1. One observation is that if every element is placed on position I, then the array is sorted, but even more so, it is sorted in a stable way. So what does that mean? Stable means that numbers that are equal stay in the same order as they were before sorting. So in the example that we just had here with the 5s, there were several 5s. Obviously, in the sorted array, all of those 5s come behind each other, but we keep the order of the 5s as they were previously. So that is a stable sorting algorithm, and that will be is a very useful property, and we'll also see later why that is useful. Okay, now let's have a look at how we can implement this algorithm. So this is counting sort. Let's have a small example next to it. So let's do, let's say we have k is 2, and we have, let's say we have 1, 0, 1, 1, 2. So that's A. And we're now going to write our numbers in an output array B. We have an auxiliary array C, which we're going to use for all of the counting that we're planning to do. Because what do we do here? We start with this array, initializing this array C as all zeros. So it will have, so here we have C, it will have a position for 0, 1, and 2, and we're going to write zeros in there. What we're going to do next is we're going through A. So we're looking at all elements of A, and for each number that we see there, we increase the corresponding number in C by 1. So for this 1 here, we're going to write a 1 here. For this 0 here, we're going to write a 1 here. For this 1 here, we're going to increase by 1 here, so we get a 2. For this one, we're going to increase this by 3. And for that 2, we're going to write a 1 here. So after this step, C is 1, 3, 1. And what is that? It counts the number of zeros, the number of ones, the number of twos. Now this as such is useful, but will not yet solve the problem for us. So what we want to have instead, we want to know for AI, what is its position? So what is position I? And for that, what we want to have is for, let's say, the twos, we want to know how many numbers are smaller than 2. So we want to, let's say we want to know the number smaller than 2. That means we have to add up the 1 and the 3. And now imagine we would not want to know numbers, now k is larger, we want to know the number smaller than 3. Then we would have to add up whatever is on 0, whatever is on 1, and whatever is on 2. But we don't need to always do that from scratch. So the trick that we're going to use here is that we can compute the numbers smaller equal to I as the numbers smaller than I plus the numbers equal to I. The smallest number smaller to I is the number of numbers smaller equal to I minus 1. So if I compute that first, I can use that in our computation of the number smaller equal to I. And that is what is happening here. So what my C now does, so first of all, this 1 can stay. Now I say this number smaller equal 1 is this 1 plus this 3. So I get 4. And then the numbers smaller equal 2 is this 4 here plus this 1. So that's 5. So at this point, C stores the numbers smaller equal I. Smaller equal 0, I have 1. Smaller equal 1, I have 4. Smaller equal 2, I have 5 numbers. And now I can use this to move my numbers from A to B. So let's have B up here. And what I'm going to do is I'm going to go backwards through A. So starting with the 2 here. And I'm going to place that on its position. And the position of this 2 will be, so I'm going to place it at position minus 1. So the index is position minus 1. So but the position of this number is simply C of AJ. So the position of this 2, it will be the 5th number, meaning the index is 5 minus 1 is 4. So this is 0, 1, 2, 3, 4, I'm placing the 2 here. Then what I additionally do is I decrease this number by 1. Why do I do this? Or in this case, I don't have additional 2's. But if I would have additional 2's, I wouldn't want to write the 2 that comes in front of this 2. I wouldn't want to place it also at position 5 or index 4, but at the previous position. And that's why I have to decrease. So next I will have this one here, and I know I would need to place it. So its position is 4, I need to place it at index 3. So this is this one, goes here. And I decrease in C the corresponding entry to 3, so that if there's another one, and there will be another one, it is not also placed at position 4 or index 3, but one in front of that. So then I have this one, it looks up here where what its position is, 3, so the index is 2. I'm going to place it here. Now I have the 0. The 0 looks here for its positions, 1. 1 minus 1 is 0, so I know the 0 goes here, and then my 1 goes here. And now I've sorted my numbers, and not only have I sorted my numbers, but this sorting was also stable. So the ones, they were in this order, they are still in this order. So that's counting sort. Let's have a look at correctness. The correctness has actually 2 parts. Everything up to the last loop and then the last loop. So everything up to the last loop is fairly straightforward. I mean, essentially what this part does, it computes the CI. So what we want to have is exactly what line 5 says here, that CI contains the number of elements less than or equal to I. And if you would want to prove that, then you would be doing first a loop invariant proof for the loop in line 2 to get the statement in line 3, and then a loop invariant for the loop in line 4 to get the statement in line 5. So let's say we take that for granted, and the interesting part here is actually the correctness of the last loop. So again, we do a loop invariant proof. The invariant is the following. The invariant essentially says everything that we've placed so far in B has been placed correctly. That is this first part. Additionally, what we want to have from C is that Ci is a number of elements smaller than I plus a number of elements equal to I in the array from 0 to j plus 1. And let's look at initialization, maintenance, termination. Initialization, initially this is kind of an empty statement, and the interesting part is simply the second one, but that is initially it's just what line 5 already says. Ci contains the numbers of elements less than or equal to I, because here equal to j plus, I mean here we're looking at the whole array, so that is the same statement. Then in maintenance, so let's assume the loop invariant is true. That means that when we're looking at aj by the loop invariant, Caj actually contains the position of the jth element. So taking Caj minus 1 places aj correctly. This means that the first part of the loop invariant holds again. For the second part, observe the following. So here we have a case distinction, depending on whether I is aj or not. For the I that are not aj, there the number of elements smaller than I plus a number equal to I in A from 0 to j plus 1 is actually the same as in A 0 to j, so up to j minus 1. So for those, Ci doesn't need to change, and it doesn't change. For I being a j, I now have one element fewer. So I need to make sure that is, to maintain the loop invariant, I need to subtract that, and that is exactly what the loop does. So that gives us maintenance, and then for termination we don't care anymore about the second part, and the first part of the loop invariant simply tells us that we've now have everything in B sorted. So much about correctness. What is the running time? We can just go through it loop by loop. We have a loop that goes over k elements and constant time per loop, order k. We have a loop that goes over n elements, order n. Yet another loop over k elements, yet another loop over n elements. All of this together is simply order n plus k. So why is this a linear time algorithm, or when can we call this a linear time algorithm? We can call this a linear time algorithm if k is of order n. So for instance, if I have a constant number, if k is a constant, so my example is a 0 and 1 example, obviously I get a linear time algorithm. But I can even have larger k's as long as k, the size of k is asymptotically not larger than n. Okay, so what do we have so far? We have that counting sort is a stable sorting algorithm that sorts an array of n integers that live in the range from 0 to k in order n plus k time. And again, stable here means that if I had two elements that are equal in the input, then in the output they are in the same order. That's all about counting sort. Let's have a quick quiz. So let's assume my input is as here, a is 3, 0, 0, 1, 1, k is 3. So which of the following arrays corresponds to C after step 4? So after we did Ci is Ci plus Ci minus 1. A, B, or C. The correct answer is A. And why is that the case? Keep in mind, C at this point should be counting the numbers smaller equal to I. So the numbers smaller equal 0 is 2. So that's why we have a 2 here. The number of elements smaller equal 1 is 4. So that's why we have a 4 here. So the number of elements smaller equal 2. I mean, there's no 2, so that's still 4. And then we have 5 numbers smaller equal 3. Let's have a second quiz, namely the following. How long does counting sort need if we have n numbers in the following range from 0 to n squared minus 1? So linear time, n log n time, or n squared time. The correct answer is n squared. And obviously it's n squared because the running time of counting sort is order n plus k. And this is k. So k is n squared minus 1, so order n plus k is order n squared. The follow-up question here is there actually a sorting algorithm that, given numbers in this range, so up to n squared minus 1, let's say, can actually sort them in linear time? The answer is yes, and we're going to see such an algorithm next, and that is Radix Sort. So the setting for Radix Sort is the following. We again have n numbers, but now these n numbers have d digits. So here we have an example, 5 numbers. Each of these numbers has 4 digits. These digits are between 0 and 9. The digits can also have a different range. We will come to that. And we're going to refer to the least significant, so that's the least important digit, as the first digit, and the most important one as the dth digit. Now there's an intuitive way of sorting by digits, and that is the following. Assume you have books and want to sort them by author, then you're going to take you'll be looking at the first letter of the author. So you take the books with A first, then the books with B, and so on. And then within A, you still need to sort and continue. So there's a more elegant way of doing this, and this is not starting with the most important letter, so the first letter, but starting with the least important. And that is what we're going to do here. So we're not going to start by sorting by the dth digit, so the most important one, but we start with the least significant digit. So here the 8, 3, 9, 4, 3, 1, and so on. The effect of this is the following. If we start with the least significant one and work our way up to the most significant one, then the last sorting, so kind of the crucial sorting, will be by the most important digit. Now, of course, if that digit is the same, then at that point the previous sorting steps kick in. So that means only if the first, so if the d digit is the same, then it matters who was first in terms of the d minus first digit, and so on. And in this way, we can sort our numbers. So radix sort, short and sweet, simply a loop over all digits, and we need to use a stable sorting algorithm on the array A on digit I. Let's do that by example. Here we have again numbers with digits between 0 and 9 and 3 digits. We first sort based on the first digit, so the least significant one here. Meaning here we have a 0 that comes first, so 720 comes first, 355 and so on. So you see here on this digit it's increasing. Then we sort on the second digit, like this. And you see we use a stable sorting algorithm. So in this example, we for instance have these two numbers, which in the second digit are the same. They are both 3. Because we're using a stable sorting algorithm, it means that the one that on the previous digits was smaller, so here was a 6, will come first. So 36 comes before 39 in this case, or 55 comes before 57. After sorting on the second digit, we sort on the third, and in this case last digit, again using a stable sorting algorithm. So now it's increasing on the third digit, and because it's stable for those that are equal in this digit, so here we have 2 3s, the one that previously came first still comes first. So the one that previously came first, so previously we here just started 29 compared to a 55, so the 29 came first, so that means we keep 329 before 355. And likewise with the fourth here. And that's radix sort. So how would we prove correctness? That is, we have a very simple loop. This would be a simple loop invariant proof where we essentially say that at the start of iteration I, the numbers are sorted correctly based on the first, on the digit 1 up to I minus 1. Running time analysis is also very simple, but it depends on which stable sorting algorithm we take. We luckily just saw a stable sorting algorithm that works well for bounded ranges, and that is counting sort. So if we use counting sort, then we get per iteration order n plus k, where the digit, now k is not the range of the whole numbers, but the range of the digits. So if we have digits between 0 and k, so in the examples that we saw, k was 9, then counting sort takes order n plus k time, and then radix sort takes, because we have a loop over d digits, order d plus k time. So radix sort sorts n d-digit numbers where the digits take k possible values in this time, order d times n plus k. So in the examples that I showed you, k was 9. But that's actually not the setting where radix sort really shines. So let me illustrate that by taking the following quiz. Let's assume we want to sort numbers between 0 and n squared minus 1. How would you pick k? So which range do you want to take for your digits? Do you want to represent your numbers in binary, so 0, 1? Do you want to represent them simply with digits in 0 up to 9? Would you like to use digits from 0 to n minus 1, or simply digits from 0 to n squared minus 1? The correct answer is C. So we want to set k to n minus 1. So why is that the case? So let's have a look again at this running time of d times n plus k. So clearly there's a trade-off between d and k. So if I can make k larger, I can make d smaller. What does that mean? I want to make k as large as possible. Okay, what does as possible mean? I mean, the largest k would be here that I offer you is n squared minus 1. So, but if I do k, so let's do k is n squared minus 1, then actually every number just has one digit. I mean, I can just represent every number by a number between 0 and n squared minus 1. So then this gives me d is 1, but the running time is order 1 times n plus n squared. So that's order n squared. So that is bad. That is certainly not linear time. So what went wrong? I said k as large as possible, but you should stop at some point. K as long as possible, as long as it's not more than n. Because, I mean, we have the n here anyway, so there's no point in having k smaller, because then the n will be the dominating part within the n plus k. So k as large as possible is making k is setting k to n, or in this case n minus 1. Any number between 0 and n squared minus 1. So if I have a number here, let's call it a, I can write it as a0 plus n times a1 with a0 and a1 in 0 up to n minus 1. So that is, so a0, a1 would be my 2-digit representation of, actually the other way around, a1, a0. So to place a most significant one in front, a1, a0 is my 2-digit representation of a, and I can, any a in this range I can represent in this way. So in this case, so if k is n minus 1, then d is 2, and then indeed I get 2 times roughly 2n, which is a linear time algorithm. So with C, we actually get a linear time algorithm for numbers in the range up to n squared. And you can try for yourself what you would get for A and B, but there we would get more than linear time. So that is Radix Sort. I want to show you one more sorting algorithm, and that is bucket sort. Bucket sort is quite different in terms of the assumptions that we're making. That starts with the fact that we're not sorting integers, but we're sorting real numbers in the range between 0 and 1. So these are numbers of the form 0.23 or 0.75 and so on. In terms of the assumptions, we're going to make use of the floor function. So that doesn't seem that unusual. I mean, the floor function is a function that you easily have access to in Python or in any programming language. But in terms of the model of computation, that is actually a bit something to take care of. Under these assumptions, and assuming that the numbers are nicely spread out, more specifically, they are uniformly distributed in the interval between 0 and 1, bucket sort runs in linear time. So what's the idea here? The idea is that we use buckets, meaning we're going to divide the interval between 0 and 1 into subintervals. Specifically in the following way. So if I have n numbers, so here I have 10 numbers, then I'm splitting the interval into n, or in this case 10 subintervals. And for each of these intervals I will have a bucket. So my input is in A, I have an auxiliary array B, and each entry of B corresponds to a bucket, and the bucket corresponds to an interval. So the first bucket corresponds to all numbers from 0 up to 0.1, not including 0.1. The next one is 0.1 to 0.2, and so on. And now I'm just taking all of my input numbers and I'm going to throw them into the buckets. That looks like this. So for instance, 0.792 goes into the bucket from 0.7 up to 0.8. Here you see once more, so the buckets go from I divided by n to I plus 1 divided by n. So in my example, starting with I is 0, from 0 to 0.1, and so on. Now, making use of the fact that the numbers are nicely spread out, uniformly distributed, we expect that they're kind of nicely spread over these buckets. Of course, that does not yet mean, if they spread out as nicely as possible, then I would have one number per bucket. That is not necessarily the case, and in my example, that is not the case. This means, in particular, if I simply take them in the order that I get them here, so I have here the numbers starting with 0.1, here the one with 0.2, then within a bucket, they might not be yet sorted. So within a bucket, we need to actually sort the numbers. So we first throw the numbers into buckets, then within each bucket, we call some sorting algorithm, and then we can simply concatenate all the buckets. Let's look at pseudocode for bucket sort. The input is an array A, so in my example, an array of size 4 with numbers between 0 and 1. The output should be a sorted list containing the numbers of A. Now what do? N is the length of A, so N in my example is 4. We initialize an empty array B, also of length N, and the entries of B will be linked lists of numbers. So if you don't know what a linked list is yet, it's not that important for this algorithm. Just think of it as a data structure where we can kind of insert a number to it in constant time. So this is now B. And here we have now this loop where we insert AI into the list. And now this is where we use a floor function, n times AI. So what does, round it down, what does this do? So AI is between 0 and 1. If I multiply it with n, I will get a number between, I get a number between 0 and something smaller than n. If I round it down, that actually brings me exactly to this, into the interval here that corresponds to that number. So here the first interval is between 0 and 0.25, then the interval 0.25 to 0.5, 0.5 to 0.75, and 0.75 to 1, always not including the last number. So this is what this loop does. It simply throws the numbers into this array B. So we get 0.792, that is in this one here, 0.792. Then we have 0.1 goes here, 0.287 goes here, and 0.15 goes here. So that's after step 4. Now in the last step, we take each of the lists and sort them. And it doesn't really matter which sorting algorithm we take. Insertion sort seems like a good idea because we expect these lists to be short, and on small inputs, insertion sort works well. So let's assume we're doing insertion sort. So we use insertion sort on this. That will give me, it's already sorted. We're lucky. All others are of length 1 anyway, so they're also already sorted. And now I'm going to concatenate them. So I now take 0.1, 0.15, 0.287, 0.792, and that gives me the numbers in sorted order. What is the running time of bucket sort? So let's say Ni is a number of elements in bucket I. And so then the running time is, throwing the numbers into buckets. I touch every bucket, every number once, and assuming we get the floor function in constant time, that will take linear time. Now we have to sort each of the buckets. We said we are using insertion sort. So if the number of elements in the bucket I is Ni, the time I spend on that bucket will be of order Ni squared. So the running time here, as running time, I get the sum over all of the buckets, and then theta of Ni squared. What does it mean for the worst case running time? In the worst case, all numbers fall into the same bucket. That means, let's say they all fall into bucket number 0, then n0 is n, then n0 squared is n squared, then this running time is simply theta of n squared. But this only happens if the points are not nicely spread out. So what's the best case? The best case is if they're kind of perfectly spread out. It means that we have exactly one number per bucket. And that means, sorting one number takes constant time. The sum and then is linear, and then we have linear plus linear is linear. So we know the worst and the best case, but we also want to know the expected case. So if we now really have uniformly distributed numbers, so for each number, it is kind of randomly placed somewhere at uniform between 0 and 1. What in this case is the expected running time of the algorithm? The assumption that we're now making is that the probability for any number to fall into any specific bucket is simply 1 divided by n. So if I take a number, the jth number has the same probability to falling into any of the buckets. I have n buckets, so the probability that it falls into a specific bucket, let's say bi, is 1 divided by n. What does that mean for the expected running time? The expected running time is the expectation of, and this was what the running time was, so the expectation of this up here. Now this we can write as, so this part is always linear, so we can take that out. So this is linear plus the expectation of the sum or of the ni squared, which is the sum of the expectations of ni squared. So if I know how large ni squared is in expectation, I know how fast my algorithm is. So how can I estimate ni squared? The expected number of elements that fall into one bucket, so the expectation of ni, that is simply 1. Yeah, so the average number of elements per bucket is 1 because we have n buckets, n numbers, so on average that gives me 1 number per bucket. Unfortunately, that does not allow us to make a conclusion about ni squared. So it is not true that the expectation of ni squared equals the expectation of ni squared. That would be too nice. It's not what happens. I will give you more intuition about what e of ni squared is in a moment, but let's first give you the solution. So e of ni squared is actually 2 minus 1 divided by n. And if we know that, and I'll show you why that is the case in a moment, then this means e of ni squared is order 1, meaning that here we get something that is order 1. We sum over all n, so that is overall linear. Again, we have linear plus linear, meaning that the expected running time is linear. So let's have a look at why the expectation of ni squared is what I claim it is. And here's an illustration. So let's assume this is my bucket bi. And now ni is the number of elements that end up in that bucket. In my example, that's 3, but in principle, it's kind of a random variable. Now, to know what the expectation of ni is, okay, I would have to count how many balls end up in that bucket, or what the expectation of that is. So that is simply, I take any of these balls, and we have n of those. I throw them into a bucket with probability 1 divided by n. It lands in my bucket here. And that's why the expectation of ni is 1. But that we already knew. That doesn't really help us. Now I want to know what the expectation of ni squared is. So here's an interpretation of ni squared. So imagine this blue, red, and green ball are the balls that end up in my bucket. So then for ni I get simply those 3 balls. Ni squared I can get by taking every pair of balls that are in the bucket. So I combine red with itself, red with blue, red with green. Okay, it's ordered pair, so I also get blue with red, blue with blue, blue with green, green with red, green with blue, green with green. And that, if I count all of those, that gives me Ni squared. So in my example, I get 9 of these combinations. How can I count this? I can count this by splitting it up into the following sum. So if you look at the diagonal here, so I combined red with red, blue with blue, green with green. I mean, that's simply red, blue, green. So the number of elements on my diagonal here, that corresponds to E of Ni, which I said is 1. This leaves the multicolored balls. Red and blue, red and green, blue and red, blue and green, green and red, green and blue. These here. How many of those do I have? Now here we make use of the fact that the throwing of the balls into the buckets for the different balls is independent. So if I want to know what is the probability of red, let's say I have in my set of balls 1 red ball and 1 blue ball. What is the probability that I get both of those in my bucket? So that means red has to land in my bucket, that's 1 divided by n, and blue has to end up in my bucket, that's 1 divided by n, and because I'm throwing those independently, that's 1 divided by n times 1 divided by n is 1 divided by n squared. So this is a probability for any kind of pair of balls that they both fall in there. How many pairs of balls do I have? And again, I have ordered pairs, excluding pairs where both are the same ball. I have n times n minus 1 of those. Yeah, so if I have, for instance, 3 balls overall, then the number of pairs is 3 times 2, 6. And more generally, n times n minus 1. So the expectation of Ni squared is 1 plus, and this is now n squared divided by n squared minus n divided by n squared. So this is also a 1, so this is 2 minus 1 divided by n. This is exactly what we claimed. So this was a lengthy explanation, hopefully providing some intuition of how we're going, how this comes about. If you want to do this mathematically, and maybe if you're used to it, that is actually the simpler way for you to do it. Essentially what we're using here are so-called indicator variables. So we have this xij, which says aj, so in this case ball number j, falls into bucket I, or the element j falls into bucket I. And what we actually want to compute then, so we can express Ni as this sum, namely the sum over all of the balls, whether they fall into the bucket or not. And we want to compute the expectation of that. So what have we seen? We've seen a sorting lower bound in the first half, and then we saw linear time sorting algorithms, and those require assumptions. We had counting sort. There the assumption was the numbers are in a certain range from 0 to k, and then we get order n plus k as a running time, which is linear time if k is of order n. Then we had Radix Sort, which had these numbers with d digits, and then the running time was order d times n plus k, where k was the number of options per digit, and this worked nicely if we make k order n. And then finally we saw bucket sort, which worked for numbers between 0 and 1. It also required using the floor function and an expectation. If the numbers are uniformly distributed in this range between 0 and 1, we get a linear time algorithm. In the worst case, this algorithm is quadratic. So let's wrap things up with a final quiz, and that is the following. Slightly different setting, we have still n buckets, but now we have n plus 1 balls, which we throw into the buckets. what does a pigeonhole principle tell us in this case? So does the pigeonhole principle say that on average each bucket has 1 plus 1 divided by n balls? Does it say there's at least a bucket with 2 balls? Does it say there are more balls than buckets? Or does it say the algorithm runs in linear expected time? So the pigeonhole principle tells us that there's a bucket with at least 2 balls. And just a reminder, the pigeonhole principle was what we used a long time ago at the beginning of this video for proving the lower bound of n log n for sorting. So that is not related to bucket sort, but it's a nice principle. So I wanted to mention it once more. That's all for today. See you next time.